was good. I was overall happy with it. A lot of A's, B's and C's, some pretty low grades, but if I took out some of the outliers, it would even increase the average more. So the median was higher than the average. So half the class did better than average. Half the class almost got, well, half the class did get a B or an A or a B on the exam. So the breakdown, so you can see kind of where you fall in the course. I've already posted the final exam, or the final exam. I've already posted exam 4 on Blackboard, the answer key to that. So just some comments. Everything was pretty straightforward. Some of you forgot that this is actually U substitution here and didn't write the 1/5 or the 1/2. On E, some of you identified it as tangent inverse, which is great. The execution of it cost a couple of points, didn't know exactly how to get it there. The people that didn't identify it as a tangent inverse was clueless on it, so there wasn't a lot of partial credit if you didn't notice that. Taylor? Nick? Okay. There's a lot of just set up and do not evaluate, pretty straightforward. Some of you would put to 3 here, which cost some points. The dx is also very important, and some of you did not put dx. I need to know what you're integrating. If it's a setup and do not integrate, you need to have all the components of the integral, which is the integral, the bounds, the function you're integrating, and if you're integrating along the x-axis or the y-axis. We saw that this comes important later on in the exam. This was meant to be pretty straightforward. Some of you took it a little further than needed, but it was meant, can you just replace where the function's negative with minus the function to drop the absolute value? 6 was meant to be straightforward. Some of you had gone through a few more steps. I don't know if you were just getting kind of bored with setting it up and wanted to show you could go further, but it was just looking for the basic U substitution there. 7 was definitely more involved than any of the other ones. This is a basic U substitution where if U is 2t plus 1, so du is 2t dt. If I manipulate this to be the exact form I want, I get this integral. Integrating from there is pretty straightforward. Some of you forced this to be like that one that was on the quiz, where you wanted to solve for t, replace that for this t, and it got ugly. So you had the choice of integrating in terms of u and using your u bounds, or you could turn it back in terms of t and use your original t bounds. You get the same answer though. Number 8, almost everyone got to this point.
Hey, I got a question.
Yeah, go ahead.
On number 7,
Yeah.
where you change it to the u and use the u bounds.
Yes.
You got the upper bound as 4.
Yes.
Oh, because it's times.
Because if t is the square root of 3, then t squared plus 1 is 4.
But then what happens? I mean, isn't there a t out front there?
The t goes away because I have 2t dt is du. So if I group 2t and dt, that's du.
What about it then makes the radical go away? Because I took the square root of 4. I had 4 underneath, but then I took the square root of that.
We can integrate it 3 over 2.
Okay.
Yeah, when you integrate it.
You're saying like radical 3
Yeah.
times radical 3, right?
Well,
Is three.
yeah, the square root of 3
Squared
plus 1
is 4.
is 4, but that's underneath a square root. That's
No.
underneath the radical.
No, the u is the function is underneath the radical. This is my u substitution. I'm
Oh,
saying
like
u
that.
is this.
Okay.
So when I plug it in, u is square root of 2, but when I integrate that, I get u to the 3 over 2 divided by 3 over 2.
Okay.
Make sense? The answers are posted online, so you can go over. And there's different ways to write this. I could have just solved for dt, which would be du divided by 2t. So if I plug that in there, my t's are going to cancel. I'm going to be left with the 1/2, u to the 1/2 du. Most of you got to this point. Some of you didn't put your plus c's, so you were absolutely clueless on what to do when you plug in 1. And you got -7 equals 10 or something along those lines, or 7 equals 10, or c equals 7. But it's very important to know that I'm solving for the value of c that satisfies when I plug in 1, I get 10. Some of you got down to this point, and then your algebra went wrong somewhere. Some of you copied this down and put a plus 10 or a -8, and it was just a copy error. So be careful with that. But now if I plug in 1, I get 10, which is what I want. Question?
If I did with respect to x on number 11, why did you color in half of mine?
Okay, I'll get there, because you only integrated half of it. We'll get there. Number 9 is an absolute value function. Most of you got this correctly. It was the exact same one that was on your quiz, except it was from 0 to 6 instead of 0 to 4. So it's straightforward there. Some of you didn't divide through by 6, which was just finding the integral and not finding the average value. Number 10 was the setup but do not evaluate. Could you find the bounds of integration, the top function minus the bottom function dx? So this was definitely going towards the x-axis here. Number 11, which a lot of you did, is you integrated from -5 to 20 of the top function minus the bottom function in terms of x. So when you did that, you actually calculated the whole area of that shape. But I only wanted the area of the shaded region. So most of you had this. And this costs you points because first off, I only can go from -5 to 0 because my bottom function is minus x on -5 to 0. But from 0 to 20, my bottom function is 0. So you would have to add this integral to only get this shaded region. You have to break this up into 2 separate intervals to integrate because the function here is defined, my top function minus my bottom function from -5 to 0 gives me this integral, gives me this area of the shaded part here. Then from 0 to 20 of my top function minus 0 gives me this shaded region. A lot of you had the way your integral set this up from -5 to 20, you integrated the top function minus the bottom function, which gave you this extra area, right? So you needed to cut that off and integrate from -5 of the top function minus the bottom function plus 0 to 20 of the top function minus 0.
So what's the reason that we split them up?
Because the bottom function here is minus x. From -5 to 0, the bottom function is minus x.
There is no...
There's no bottom function
Yeah, oh.
from 0 to 20. Depending on the shading, if I was to continue this curve and ask for this area as well, you would have the correct setup. It kind of led, the simplicity of this was led to the y-axis, but I didn't count off if you did the x-axis correctly. And I think 2 people did the x-axis correctly. So, a lot of you had this from -5 to 20. So you can see where that is encompassing area that's not shaded. Does that make sense?
Can I get any extra points for being one of the 2 that did that?
You don't lose points, but no. So I mean, it's definitely you got your points for having it, but yeah. Question?
Can be a blank exam for me?
No. Yes. Nick. I'm sorry. Anyone else in their exam that snuck in? Okay, so the point of today's lecture is to kind of give you guys an idea of final exam or what to kind of study on the final exam. Hopefully you've been doing that in the last couple of weeks, maybe the last month, printing off final exams, going through them. They're posted on the website. They're also posted on Blackboard under Calculus Resources, organizations in which you are a member, not under our calculus page for our class. You have to go into Blackboard and under, so let's just do that real quick. Blackboard, you sign into Blackboard. You have your courses listed under your courses, but under My Organizations is the Calculus Resources. Yours says, I think, organizations you're a member. So this is Calculus Resources, Calc 1. It gives you some old final exams and the solutions to that. So, one of the first things I want to talk about on final exams are the instructions. See if I can find one that's current. So, you're asked, write your name on your paper, your instructor's name, and the time your class meets. Only scientific calculators will be allowed. So I've been lenient this semester on, I don't know if you have a graphing calculator. I don't really care too much. You're going to have to show your work. And graphing's not, a huge part of my written exams. But if you bring a graphing calculator to the final, you'll be asked to put it away. And if you use it during the final exam, they'll take your exam. So it's something coordinated through all the classes. So if you've been using your scientific calculator, just be prepared, you won't have it on the final exam. Make sure your test contains all the problems that are on the cover page. This really isn't an issue, but it's kind of also saying it's your responsibility to make sure your page, all your final exams there. So when you get it, go through and make sure there's 18 problems or however many problems are on this front page. Usually, and I don't know, whoever's the coordinator for this semester, I don't know if there's any multiple choice. But if there's multiple choice, it's all or nothing. So you don't necessarily have to show your work because we're not going to look at it. You're not going to get partial credit. So you want to make sure you double check those because it's all or nothing. So make sure if it's 1 over something going to 0, what that means. All other pages, you must show your work to receive full credit. If you have the right answer and no supporting work, you're not going to get any points from the instructions. And whoever grades that may or may not be more lenient or maybe harder than what I am usually grading it. So they're going to ask you to simplify. If it doesn't say simplify, simplify. So if it specifically asks you not to simplify, you're fine not simplifying. In all other cases, you need to simplify. An example on this last exam I gave you, if you had 20 over 5, I let you have the points for that. But on the final, you need to write 4. You need to put that, or you're going to potentially have a chance to lose points by the instructions. There will be cases when it says find the derivatives, do not simplify. That's the only case when you don't have to simplify. No approximation, so do not plug square root of 3 in your calculator and give us 1 point blah, 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 blah. Just leave it as square root of 3 if that comes up. And then write your final answer in the box provided. I try to get you to box your answers as you go. Sometimes you'll apply a different technique or method to the same problem and get a different answer. Box the one you want us to look at, because as we're grading 400 finals, we get a little cranky when there's 3 different, work. One of them's correct, the other 2 are wrong, and we're not going to necessarily pick. If you integrate sine and you put cosine, and then you integrate sine and put sine or some minus cosine or something, and you don't indicate which one, we're just not going to give you points. So on the final exam, there will be boxes for you to put your answer in.
So we shouldn't get any weird decimal numbers on the final exam.
You shouldn't. No, it should be pretty straightforward. You shouldn't have anything crazy.
Okay.
But it's pretty straightforward. So calculators aren't that beneficial. So anything you're using your calculator on too strenuous, you're probably not approaching it correctly. So another kind of technique I've seen students be successful with in the final exam is they work it backwards. Because the beginning couple of pages are the stuff we did 4 months ago. So sometimes students will start working it frontwards and get confused, or they'll get upset because they're not remembering it, and then that throws off their mojo for the end. So I'm not saying do it that way, but just depending on the type of student you are, don't be afraid just to flip to that last page and work it backwards, because that's kind of how you're remembering calculus. A lot of times you're not remembering it from chapter 1 to chapter 6, you're remembering it from chapter 6 to chapter 1. So in the past, all the final exams have been follow the same path as we took through the course. So the beginning stuff will be the stuff we started with, and the end stuff will be the stuff we end with. Occasionally, they'll think the exam's a little short, and they'll put a question at the end that probably should have been in the middle, but that doesn't really happen too often. But definition of the derivative, in the last couple of semesters, I've seen it show up.
I saw that at the end.
Yeah. Here's, by the way, we're going to throw this one in there. And this would maybe be more at the beginning. And it just kind of depends on the coordinator and how they compile it. Generally, though, it starts off with limits, goes into continuity, goes into the equation of the tangent line or local linear approximation, talks about derivatives, talks about local maximums and minimums, intervals of increasing and decreasing, graphing, applied problems, related rate, maximum and minimums, and then it goes to integrals, and then application of integrals, being able to compute integrals, and then chapter 6, which would be the area between two curves. So things that have shown up in the past, and I've kind of alluded to these during the semester. Definitely limits, the end behavior. Limits 0 over 0 or infinity over infinity. In the beginning, if they show up in the first couple pages, there's always another way to do it versus L'Hopital's rule. So in this example, you can factor it. Right side limits and left side limits always exist, but the limit at a point may or may not exist. So if they give you a right side limit or a left side limit, you're always going to be able to write, it's going to be something other than does not exist. But if this was dropped, it's possible that the limit's not going to exist. Continuity has shown up. Find the values of k in which the function is continuous. So the limit on the right has to equal the limit on the left has to equal the value of the function at that point. Solve for the k that satisfies those conditions. Equation of the tangent line has shown up. And really I've seen it show up in two different applications. Local linear approximation is an equation to the tangent line. So they say approximate 4.02 squared. So you get the equation of the tangent line around the point 4 and then plug in 4.2 minus 4 from that x minus x naught, right? This is a straightforward, find the derivative and plug in 4 to get the slope. You need a slope and a point. So you're only given an x coordinate, but to find the y coordinate, you plug that into the function, right? So you have x comma y, and you have a slope. So then you use the point slope form, and then more specifically, they ask you to solve for slope intercept form. So then you're going to have a y equals an mx plus b in your box. There's usually a page of just derivatives. The quotient rule, the chain rule, the product rule, the derivative of e to a power, ln of x, sine of x, cosine of x, or any multiplication of trig functions, polynomials. So here's an example of the product rule. Here's an example of the chain rule. Here's an example of the quotient rule. So knowing each one of those proper formulas is important, and then being able to apply them. The derivative of the first function, hold the second one, plus the derivative of the second one, hold the first one. The derivative of the top, hold the bottom, minus the derivative of the bottom, hold the top over the bottom squared. The derivative of the outside, evaluated at the inside, times the derivative of the inside. I've seen where they've specifically say like a hint, use logarithmic differentiation. I've seen when they've not told you to use logarithmic differentiation when you need to know to use logarithmic differentiation. So this is an example of logarithmic differentiation. They may or may not tell you that. But anytime you have a function to a function power, you're going to use logarithmic differentiation. Implicit differentiation, generally I've seen shown up in the past. Students lose points on algebra on this one a lot of the time, so be careful. And then also know you're looking for dy dx. So the derivative of x is 1, but the derivative of y is dy dx. So use the product rule. So you have the derivative of x, which is 1, hold y, plus the derivative of y, which is dy dx, hold x. But when you take the derivative of y squared, that's 2y times dy dx, right? Derivative of the outside evaluated the inside times the derivative of the inside. And then they want you to find dy dx at the given point. So once you have the function for dy dx, you plug in x is 3 and y is 1. Evaluate the limit. Generally, when you're halfway through the exam and you find a limit, it has to do with L'Hopital's rule, right? So in this case, this is infinity over infinity. What is the correct answer here? 0, right? However, it says, show all the work involved. So you need to write something other than the answer. If you write, from the theorem, a polynomial over an exponential, as x goes to infinity goes to 0, that's all. You could write that, or you could just apply L'Hopital's rule a couple times here and see that you're going to get 6 over something going to infinity, which is 0. So be careful on stuff like that.
E to the x over a function is
A polynomial over an exponential is always going to go to 0. An exponential over a polynomial, as x goes to infinity, goes to infinity. Right? Because an exponential, basically, you can't ever get rid of that by differentiating it. And a polynomial, you can differentiate enough for it's a constant.
Like, even if that was x to the 100, right?
Yeah, even if it was
0,
x
right?
to the 100,
Yeah.
it would still be 0. Question?
Yeah, just back up a little bit on the differentiation of the trig functions.
Yeah, like derivative sine, cosine, tangent, secant,
Yeah,
cotangent.
I know that we touched on that later on, and that was
Integration, that was
integration.
backwards.
Okay.
So if you know those 6 derivatives, you'll know those 6 integrals.
Okay.
Yeah, and all 6 of those are free game, as well as derivative of tangent inverse and sine inverse are free game.
Just those.
Yeah,
inverses.
just those inverse, sine inverse and tangent inverse. This one's a good application of the derivative of ln of a function in L'Hopital's rule. So you take the derivative of the top, which is 1 over the inside times the derivative of the inside. The derivative of the bottom is just 1 over x. So you have a fraction divided by a fraction, flip and multiply, and simplify. Intervals of function increasing and decreasing. So if you're having a polynomial, pretty straightforward. Take the derivative, set it equals 0, and then test the intervals in which the derivative is positive or negative. If the derivative is positive, your function is increasing. If the derivative is negative, your function is decreasing. Concavity has to deal with the second derivative, going about the same thing, right? If the second derivative is positive, I'm concave up. If the second derivative is negative, I'm concave down. Local maximum and local minimum, you can either use the first derivative test or the second derivative test. If you have a function that the derivative is positive on one side and negative on the other one, you have a local maximum. If you have a function that the derivative is negative on the left-hand side and positive on the right-hand side, we have a local minimum, right? If you just take 2 seconds and draw a picture, you usually get maximum minimums, no problem. So here the work is really shown in part A or B. Related rates. Probably the last 4 final exams or more has had a related rates problem on there. Generally there's 2 to 3 application problems. Related rates and maximum minimums are the 2 main sections we take application problems from. This one's the latter problem. I've seen oil spill problems. I've seen sphere problems. So if I'm blowing up a volume, if I want to change the rate of change of the radius, the rate of change of the volume, or the rate of change of the radius of the circle to the rate of change of the area.
That equation going to be given.
The volume for the sphere would be given, but not the area of a circle.
Okay.
I've seen in the past where they've given, by the way, this is the area of the circle, but it's not a guarantee. Yeah, you should know that. Another thing, maximum and minimum. So I could say, here's a box with this given volume, minimize the surface area. Here's a box with a given surface area, maximize the volume. Cost of a fence, it's going to cost me this much money to build this fence. Or I have this much money to build this fence, I want to maximize my area. If I'm next to a river, just know how to set up those problems. Graphing, there's probably anywhere between 6 to 12 points in the final exam that something has to do with graphing. Either here's a function, graph the derivative, or here's the derivative, match that to the graph of the function, or here's some information and sketch a graph. So this example has quite a bit of variation. The function's defined and continuous. It means you can never pick up your pencil.
Could you do this one real quick?
Yeah, so let's just graph an example of this. The function is defined and continuous. It's differentiable everywhere except x equals 0. So I know at x equals 0 I have some corner. The limit as x goes to minus infinity of the function goes to infinity. The limit as x goes to infinity goes to 4. So I'm going to approach this line either from top or bottom. I haven't really decided yet. The solution to the equation, the derivative of the function equals 0 at minus 4 and minus 2. So at minus 4 and minus 2, the derivative equals 0. So it means my slope is 0 there. So I have a maximum or a minimum. The solution, sketch below a graph of the function that satisfies all the above requirements, making sure your graph clearly illustrates them. So I have some freedom here. I need to know that the derivative equals 0 here, and the derivative equals 0 here. So I could go ahead and say, okay, I'm going to have my function look like, does it say, say I have, so my slope's 0 here, my slope's 0 here, and the limit is x goes to, ooh, there's a corner here, so I want to put a corner here.
You cross below the
Yeah,
horizontal.
yeah, that would be good. So I could be like this. There's multiple variations of it. It's a little, okay, the solutions to the equations are this, but it doesn't say only are this. So, I mean, you could go, down here. As long as you satisfy the requirements, the slope 0 here and the slope 0 here, unless it says the only points in which the solution of the equation equals 0 are these 2 points. But it doesn't
Why
necessarily
was
say
it
that.
you had the V part? I forget.
Because it says that the function is differential everywhere except 0. So I have to have some corner there. Some like absolute value function.
Would that be at the origin specifically, or just
Wouldn't have to be.
where x is 0? Anyway?
Yeah, it could be like this.
Okay.
Could be just as long as x is 0.
Okay.
So my function's continuous everywhere, and it exists everywhere. I never pick up my pencil, but it's the derivative doesn't exist at x equals 0, and the derivative is 0 here and here because the slope is 0 there.
How would it ever give you a specific point, like where it's not differentiable? Instead of saying like x equals 0, it's not differentiable at like this point, I guess.
0,
Would they do
5?
that? Yeah.
Possibly. I mean,
And then you have like a specific.
then you
spot.
would know that point needs to be a corner. I've seen applications, and I've given you one, or I've pulled this up in class with something like this, where on top of the end behavior, and here's the limit as x goes to minus infinity and infinity, so that has to do with end behavior, horizontal asymptote. This has to be the limit at 0, so automatically I know it's not continuous at 0 because the limit on the left doesn't equal the limit on the right. And then I have to deal with these increasing, decreasing, concave up, and concave down functions. But I should know I'm going from a negative slope to a positive slope, so I should have a minimum at x equals 2. And then I'm changing concavity at these 2 points. So I'm concave down, I'm going to drop water. To concave up, I'm going to hold water. My function is either increasing or decreasing there. So these are a little bit more limited on all the different variations, but as long as you're meeting these criteria, you're going to get all your points. So there's a little bit more criteria here
Where was
with
the
concavity.
asymptotes on that one?
Well, this is not really an asymptote because it's the end behavior is going to infinity. So when the end behavior approaches a limit, that's called a horizontal asymptote. So there's only one asymptote here.
How'd you know put that one in there?
Because it told me that the end behavior as x goes to infinity approaches 4. And as x goes to minus infinity, that goes off to infinity. So if you kind of just sketch out your axes and say, okay, what do I have to do? And then just connect what you can. So graphing is usually, like I said, anywhere between 6 to 12 points in some aspect or another. Minimum and maximums, I think I gave you this exact one on an exam. So if I want to find the absolute minimum and the absolute maximum on a closed interval, I have to find critical points within that interval, test the critical points and the endpoints, and then come up with the solution. Integrate. This is a basic U substitution. It is not sine inverse. So be careful. Sometimes people see a square root in the denominator and they throw it out there. But pretty straightforward U substitution, integrate in terms of U, and then back substitute in terms of X. So your answer is a function of X.
Is that what did it say that in the instruction?
Nope.
So could we
Find the
leave it
integral.
in terms of U or no?
Yeah, that's the only way to do it. You cannot leave it
No,
in
I
terms
mean,
of U.
okay.
But yeah, this is a U substitution.
So unless something said that you could.
You can only leave it in terms of U when you have your U bounds, when you have bounds. This
Oh,
is an
yeah,
indefinite
okay,
integral.
yeah.
So you need a plus C here,
Sure.
right? A particle with a given velocity along the x-axis, find the position, and satisfy the equation. When you plug in 8, you get 0. So you're going to integrate it. So you have the function plus C. Set that equation equal to 0 when t is 8. Solve for the value of C that satisfies that, and then write your position function. This is another example of a U substitution. Here you can leave it in terms of U as long as you change your bounds of integration from 1 to 2. Integrate in terms of U and plug in your U bounds, or integrate in terms of U, take it back in terms of T and use your original T bounds.
You do get a final answer on that. Like
Yes, you get a number
You get an actual, like, it's the area.
because it's an area. Find the total area between the graph y equals sine of x and the x-axis over the interval from 0 to 4 pi over 3. So they've bounded the function with the x-axis. So the total area. So this is the absolute value of sine. So you have to break that up to find the integral from 0 to pi, so that's going to be positive, and then add that to the area from pi to 4 pi over 3, which will be negative. So you need to add the absolute value of that. Does that make sense?
Can you write that down, please?
So, let's see where we're. If I was to,
Well, doesn't, because if you set that equal to 0,
this is the graph of sine. And this is 2 pi. This is pi, sine. And if I want to integrate from 0 to 4 pi over 3, which is pi over 3 past pi, this is 4 pi over 3. If I want to find the total area, between the graph y equals sine of x and the x-axis over the interval. So total area is kind of like the difference in total distance traveled versus displacement. If I just integrate this, I'm going to take this area minus this area. So I need to break this up 0 to pi of sine of x dx, really minus the integral from pi to 4 pi over 3 of sine of x dx. Or you can just take this area plus this area. So you integrate this, you plug into upper bound minus the lower bound. You integrate this, the upper bound minus the lower bound, and you add those two areas together, the absolute value of those two areas together.
When I practiced this one on the test, I did it where, like, I mean, basically it's pretty much the same way. That one plus that one, but it's the negative of that one.
Yeah.
So it's basically the same thing as
Yeah.
minus.
Negative of a negative is a plus, yeah. So
Oh, okay.
you can do it multiple ways. Some people will say, okay, find this area and make it absolute value. Find this area and take the absolute value and add them together. Or take this minus this. This is being negative, so you're adding it. So as long as you're consistent on what you do, it's fine. To know that this area is going to be positive and this area is going to be negative. So the net area would be this minus this, right? So it would be this plus this. This area plus this area.
That would be a distance traveled.
That would be total distance traveled, yeah. So if it asks for the total area, that's what it's wanting. If they just say find the area between 0 and 2 pi, you're going to know it's 0 from the graph. But if it says find the total distance traveled, the particle starts here and ends in the same spot.
Yeah,
So
so its displacement
would
is
be
0.
0, but the
Over
total
over
distance
that.
traveled would be this area plus this area.
Right, okay. So it's just, so I can see, it's just in the wording of the problem.
Yeah, and they try to also kind of give you a hint that you're just not integrating this from 0 to 4 pi over 3.
Okay.
You have to break that up. Definition of the derivative has usually been on the final exam in
Is this usually where it shows up? Or
Not
kinda
really.
everywhere?
In the past, it was just kind of an added-on thing, and now I think it's more consistent, so
Yeah.
it goes where it originally shows up. The definition of the derivative is the limit as h goes to 0 of f of x plus h minus f of x over h. Not explaining to me what you do. I've graded this problem the last couple of semesters, and students will be like, they know that the derivative would be x to the minus 3, so then they try to explain how they got that by like,
Defining it?
like writing it out, like, oh, you take the power down minus 1 to the, like, don't do that. Start with the definition of the derivative. This is the definition of the derivative. A lot of times you know the answer, but it will tell you no credit will be given without supporting. Here it is.
That you know that
Use
That's
the
pointing that you know what the definition is.
warning. No other formulas for derivatives may be used in this problem. So everyone at this point should tell me the answer is 6x minus 1. But you need to show that algebraically. So we're looking. Do you know the definition of the derivative? If I plug in x plus h, I have 3x plus h squared minus the quantity x plus h minus the function of x divided by h. So be really careful with distributing your negatives. You know the right answer. So just make sure you get from point A to point B. Basic derivatives. Find the first derivative, find the second derivative.
So nothing on 6.2?
6.2 will not be covered on the exam, right? So I got that email saying that the exam will cover through 6.1. So I let you guys know that. So in the past, it had been covered. So if you see, this is actually 6.4, which wasn't going to be covered anyways, but sketch the region, evaluate by rotating a solid. You're not going to have that type of problem. You will have a problem from 6.1 though. So find the area between two curves. And it might ask you, have you go through and calculate it. So setting that up is crucial, because if you don't set it up correctly, you're not going, any calculation is going to be pointless. This is another u substitution. So if u is x squared, you get 2x, so dealing with a constant out front, simplifying that, changing your bounds of integration and integrating in terms of u, or going back in terms of x and using your original x bounds. Find the area bounded by a quadratic and a line. You guys have done that, right? Set that up, integrate it, plug in your upper bound minus your lower bound. This is a u
So 6.1
substitution.
right there?
Huh?
That last one was 6.1?
This is 6.1.
Yeah.
This is a u substitution. U is just kind of, u is sine of x. The derivative of sine of x is cosine of x dx. So this exactly goes away to be du. And then you have u to the minus 3, integrate that. And then you always want to make sure in a definite integral you put your answer back in terms of x and put a plus c. Right? And an indefinite integral, you'll have bounds. Sorry, I switched those. In an indefinite integral, you want to turn it back in terms of x and put plus c. On a definite integral, you'll have bounds. Your answer will be a number. You don't have to always go back in terms of your original variable. This is straightforward 4 times tangent inverse of x plus e to the minus 3x divided by minus 3 plus c. Right? You guys have done an example of this one. Maybe this exact one. I don't know. I have limited creativity on making exams sometimes. So, find the intervals in which the function is increasing. More than likely, I've always seen a polynomial times e to some power. Knowing how to differentiate that correctly, right? The derivative of e to the minus x squared is e to the minus x squared times minus 2x, right? The function is e to that same power times the derivative of that power. E to any power is never 0, so you can always factor that out and just ignore it. And it's always positive. Question?
It's got a constant in front of it, does it just go away?
And you differentiate it?
Yeah.
You
So it's
no.
5e to the negative x.
If it was 5e to the minus x, the derivative would be 5e to the minus x times minus 1. So yeah, that constant stays out front, right? Remember the theorem, the derivative with respect to x of a constant times a function is the constant times the derivative of that function. You can think of it as the product rule as well, and the derivative of c is 0. Hold f of x times the derivative of f of x, hold c. Question?
The definition of the derivative,
Mm-hmm.
so that's that right there.
Yeah.
We'd have to write that out.
Yes. So if I ask for the definition of the derivative for x squared, you know the answer is 2x, but you need to write the limit as h goes to 0 of x squared plus 2xh plus h squared minus x squared over h, right? This would be x plus h squared,
Yes.
and this is f of x So the x squareds cancel. If I factor out an h, I'm left with 2x. Right? You guys remember doing that? So I'm a little bit sloppy, but this is f of x plus h minus f of x over h. The whole goal is to factor out an h to simplify this h in the denominator to get your answer. Make sense?
For number 10, we do logarithmic differentiation and pull it down.
Would it be beneficial to use logarithmic differentiation? Not really, because you could. It would be sloppier, though. It would be quite a bit sloppier if I look at logarithmic differentiation. Let's see.
So that's
Possible.
This is a product rule.
Because, yeah, just the product rule, derivative of the first function, hold the second one plus derivative of the second. Because if you have y equals x e to the minus x squared, if you use logarithmic differentiation, you get this.
Oh, okay, okay.
Yeah, it's terrible. It's not impossible, but what do we end up with? Derivative of this function, hold this one. What's the derivative of this function, hold? Yeah, it's here. This could be broken up to ln of x plus ln of e, and ln of e is 1. Yeah, but so no, don't do it. I don't want to grade it. If you try to do that, I'll just like bang my head against the table. Does anyone have any questions? Do you guys kind of know what to expect?
Why go over, one of the first limits, please?
Before L'Hopital's rule.
Yeah.
Really long.
Okay, so let's look at these two. Both these concepts have the potential to show up. The limit as t goes to infinity of sine of t over t. Well, sine of t oscillates back and forth between plus or minus 1, but it's always bounded, right? So it's just some number between minus 1 and 1. If t is going to infinity, I have some number over something going to infinity. Some number divided by something going to infinity, which would go to 0. So sometimes on limits, you can also plug in points to get kind of an estimation of what's going to happen. If you plug in enough, this is going to go to 0.
I just felt like when we did it a long time ago, I mean,
There's more work into it.
a lot of work, but
Yeah.
we can almost like, could we apply L'Hopital's kind of like
You
that?
can't apply L'Hopital's rule here because it's not infinity
It's
over
a
infinity.
But we know it's a constant over infinity, so that way we know it's
It goes to 0.
So we can evaluate it like that because, or do we have to
So-
do more work?
Limited.
A lot of times on
I think
the...
with L'Hopital's rule you have to show work, but with the beginning limits you don't have to show
Correct, because there is more than one. A lot of times the beginning limits have multiple choice, so it doesn't even matter the work shown here. This example, this is a good one. This is, you could use the L'Hopital's rule because we do have 0 over 0, right? So I could do L'Hopital's rule, or I can factor it. So if I have this one, I have the limit as x goes to 2 from the left of x minus 2 over x squared minus 4x plus 4. If I plug in 2, I get 0 over 0. I could apply L'Hopital's rule, or I could factor it. Turns out this is the limit as x goes to 2 from the left of x minus 2 over x minus 2, x minus 2. So these cancel, and you're left with the limit as x minus 2 from the left of 1 over x minus 2. This concept comes up a lot on the final exam, or it comes up on a lot of the final exams. So here, if I think of my number line, I'm on the left side of 2, so I'm less than 2. So if I have a number less than 2 minus 2, it's going to 0, right? One over something going to 0, but it's always negative. Right? So that's going to go to minus infinity.
Could you just put like 1.999 in the original problem and kind of see where it's going?
Yeah. You could plug in some points to kind of see where it's going. Be careful on that and make sure you're plugging in correctly in your calculator. That's something that I've seen go wrong. But yeah, it's going to minus infinity. You cannot use the power rule on this one because it is not an end behavior. So some people say, oh, this is going, 1 over something. This is not going to infinity. If it was going to infinity, your answer would be 0.
So what would
L'Hopital's rule would be the limit as x goes to 2 from the left of 1 over 2x minus 4.
Because you take the derivative of the top.
So this is still going to 0, but it's always negative. Because minus 4 is always larger than 2 times a number less than 2. So 1 over something going to 0 but negative is minus infinity. Make sense? Alright, so I will send out an email later on today confirming that I will be in the ILC, and then also letting you know the date and time and location of the final exam. Saturday at 10:30, I think. And then I think it's